We studied universal gravity this marking period. Look at your equation sheet and see if you can find the equation for universal gravity.
Oh yeah.
Yes.
One M2 over
All right, Gina, now look. Pretty good. Over R squared, yep. Yeah, so it is under the heading of gravity, force through universal gravity. G is a constant. M1 and M2 are the two masses that are pulling on one another gravitationally over R squared. G is this. I think in your book it's like 6.67 some times 10 to the negative 11th. It's the same thing as 2/3 times 10 to the negative 10th. Don't be confused by that. It's just where you put the decimal, okay?
Thanks for writing in the unit.
No problem. The universal gravity happens anytime any two masses interact. However, it is only appreciable, measurable, when masses are what?
Really big.
Right. So, the most likely type of problem that you would see would be one involving two, like, celestial bodies, like a binary star system, or a star and its orbiting planet, or a planet and its orbiting satellites. Got it? So that means that universal gravity is useful in the universe if you equate it to centripetal force. Why?
Because centripetal force is the center-seeking force, which is also the same as gravity, because without gravity, things would be able to be held together.
Yeah.
So,
And when we're talking about big stuff, planets and stars. Right.
If it was almost any of the centripetal forces, centripetal force equals another force, so it would be like gravity, friction.
Yeah. Yeah, and this kind of allows me to double dip. So let's do a problem, I don't know, kind of like what you're going to see tomorrow. Here we go. Yeah.
Yes, I had to explain the closest to that was awful. I had to explain what we want was. Yeah. Oh my God. So it's basically implying a sexual
All right. What's the name of that?
It's wink walk. It's to imply a sexual innuendo for something.
Like when you use a little, like, icon thingy? Like a little winky face? Is that what you're talking about?
End a sentence with it. Like, if you say something that would otherwise be taken as an innocent statement to imply something of that nature. Like they were being friendly with each other, wink wonk, would imply more than friendly.
You actually add the phrase wink wonk at the end? That's a thing?
Especially awkward teenagers.
So, in my day, we would have said, if you know what I mean.
Yes, exactly.
Got it, all right.
If you know what I mean.
All right. Right.
Yeah.
Yeah. And any teenage boy can turn anything into, right?
Precisely.
Okay.
Like, you could be like, so yesterday I was doing my homework, and they'd be like, I don't about that, man. And you're like,
exactly. All right. Okay. In the universal gravitational equation, sorry I got sucked into that whole thing. If you know what, never mind. Very sorry for that.
all the catching you do on teenage boys, and then that. I don't know what to think.
I'm sorry! Why one big mass and one little mass? I can't think of anything now. Right. So if this is a planet orbiting a star, the big mass is the star, right? If this is a satellite orbiting the Earth, the big mass is the Earth. So the reason we differentiate is we can get rid of the little mass. So that's the orbiting mass. That's the orbiter. This is the orbitee.
So the small mass is just.
You don't need it, right? Yeah, it kind of depends on which of these equations we're going to use.
Wait, what's the big mass?
The big mass is the central object, so like the sun versus the Earth. That would be the sun. Or the Earth versus like a communication satellite. Okay? So now let's say that we have, I want to solve for the mass of a big planet, okay? Or a star. And at a radius, so that's our unknown, at a radius of 4.9 times 10 to the 9th kilometers, it takes 90 days for one complete orbit. And we usually use, by the way, a capital T, not to be confused with fancy T, or T for tension, but a capital T to represent period, and it's like anything that's cyclical. So when we get to simple harmonic motion right after exams, we're going to use this quite a bit. So it's the time it takes for one cycle. So like for the Earth to go around the sun, what would capital T or period be? 365 days, that's right. Why did this stop? Oh, it didn't stop. Okay, so that's what you're given. And yeah, from that you've got to be able to figure out the mass of the central planet or the star. That's going to be the larger mass. Now, since we're talking about objects that are orbiting, would it be better to use the linear velocity version of centripetal or the angular version?
Angular.
Yeah, I would agree. So let's, and that's why we're not going to cancel a radius, because the radius is in the numerator in this particular version, okay? So we're solving for m, so let's rearrange this for m. We're solving for mass of the planet. That will equal, oh, and little m canceled. Let's see, omega squared r cubed over big G. Do you see where that came from? I solved this for capital M. Now, the only tricky thing about this, we know the radius, right? And we know G, that's a constant. So the tricky thing here is how do we figure out the angular speed as the orbiting whatever is hurtling through space? Yep, right, that's correct. Use that 90 days and convert it to radians per second. So, because of time, I'm going to just do that for you. So, in 90 days, how many times around? Once. Or, in radians, 2 pi, right? So that's that one time around, 2 pi radians takes 90 days. So that's going to give you angular speed once you do some vector label. 1 day, 24 hours, 1 hour, 3,600 seconds. And when you solve that, you end up with 8.1 times 10 to the negative 7th radians per second, which seems ridiculously small, right? But it's actually not, because radians are like slices of pie, right? A radian is like a pretty normal slice of a pie piece. But this is a humongous pie, right? Yes. So since it's such a big piece of pie, you have to go through a small amount of radians, otherwise you're breaking the laws of physics and traveling over the speed of light. So that's why it's so small, okay? So now we have omega, we have r, we have g. Hey, let's solve for m.
Yay.
So m will be 8.1 times 10 to the negative 7th radians per second, quantity squared times the radius, 4.9 times 10 to the 12th meters, quantity cubed, over, yep, good, 2/3 times 10 to the negative 10th. Everybody see where that 12 came from? I took this. I took this, because you weren't the only one who didn't know that.
Oh, I know.
Okay. Just the only one brave enough. Man enough to admit it.
I didn't know.
So, he's still more of a man than you are. So, 9 to 12 is the extra 3 zeros to go from kilometers to meters. Because there's 1,000 meters in a kilometer. That's the 3 zeros. Okay. Okay. So I'm going to just type this into my calculator, and then we got to go. We got to keep going. And this is kind of a hassle on your calculator, so make sure that you can type these big numbers in and square them and cube them and get the right answer. I got 1.16, or about 1.2 with 2 sig figs, times 10 to the 36 kilograms. Does that make sense for a star or a planet? Yeah, it should be big. Anybody check my calculator button pushing? You got it? Okay. That's good news. All right, I'm going to, 1.2-ish times 10 to the 36. I'm going to go over something that's both review and new-ish. It's pretty easy, so I think what I'm going to do is make it extra credit on the marking period exam. So we have time, maybe. What time? When are we done?
We got 5 minutes.
We have 5 minutes. All right. Let me tell you the last 2 free response. One of them, this is going to be super fast. You ready? We did momentum problems. Collision problems? Okay. Pool table physics, remember those? So the one on the marking period exam is going to be easy. It's going to be one of these. Remember, they either collide and bounce off or collide and stick to, all that kind of thing. It's going to be one of these. This is inelastic.
That means they stick.
They mean they stick.
I like it.
So remember, you conserve the momentum horizontally and vertically. Does this look familiar?
Yes.
So point with your physics pointing finger the direction of the combined mass after they collide. Bam, baby. Look at it and see if you understand.
Yes.
Yep, that's fine. And I didn't solve this, so let me do that real quick. $53.
Inelastic.
So these are the answers. So it's a 3 kilogram meter per second horizontal momentum, 4 vertical, and then 5 momentum is the resultant. Then you have to divide by the mass to get the velocity. Okay? And I am recording this per this table's request, so this will be online if you want to check it. Okay? Tommy?
Is this extra credit on?
Nope. Yeah. Dang it, you had this one. All right, so here's the extra credit. Ready?
Yep.
Okay.
Wait, where do you get the 4 from?
Okay. 1 meter per second at 53 degrees. All righty, so here's an extra credit problem for the test. Skaters at the end of their long program. So feel free to chillax, and if you really understand this, do it on the test. If you don't, skip it. If you want to give it a try, it won't hurt anything, okay? Skaters at the end of their long program oftentimes do a spin, right? And they do it at the end because they go really fast and they get dizzy. So that's why they wait till the end. typically they start spinning slowly, and then they do some kind of magic, and they speed up, and they spin really fast.
Right.
Yes, they use Jesus fish to get there. Do I have any gymnasts? Divers?
Does anyone here
Ice skaters? What kind of, do you figure skate? Oh, dang it. All right. I have cheerleaders in here. You guys do gymnastics, so I'm putting you on the spot here. And Bailey, you're on the hook for this one. In which body position do you rotate faster, when you're doing a back tuck or when you're doing a back handspring? Oh, look, a whole room full of cheerleaders. Thank you. Yeah, okay, you're trying out in the fall. So, the reason... You were a gymnast?
I was.
Wow! Well, at, like the old Sunset Coast Gymnastics or something? Or like out at... Really? Wow. All right, we got to go fast. Here we go. The reason they spin faster...
Yeah, guys, that part's so cool.
Stop talking.
Let's see a more paperwork.
The reason the skater spins faster is because they start with their body position open. So that would be like more like a back handspring or a layout, right, Graham? Right? Full body laid out position. And then they pull their arms and sometimes their legs in. They tuck they change their shape. They don't change their mass unless, like in Blades of Glory, they lose body parts. So they pull their body in. That changes the shape. And you can't get something for nothing. So by changing shape, by making the moment of inertia smaller, something has to increase, and what is it? Velocity. So here's the equation. It's really easy. Angular momentum in equals angular momentum out. L is angular momentum. That's the symbol we use for angular momentum. Angular momentum. All right. So angular momentum in equals angular momentum out. Momentum is mass times velocity. The rotational analog for mass is I. The rotational analog for velocity is omega. So think of the skater. Arms out. Big moment of inertia. Big moment of inertia. Slow speed. Pulls their arms in. Pulls their arms in. What happens to moment of inertia? It gets little. What happens to their speed? It gets big. That's it. Well, I'd have to give you 3 out of the 4. Or I could do it more conceptually, as follows. Let's say that as the skater spins, and we used to do this, like my kids when they were little, swings. You know how you can make a swing spin, like, and so I would have them spin on the swing with their arms and legs out, and then spin them, and then pull their arms in and their legs in. Annie could do it really good because she could make a tiny, tiny ball and like spin super fast on the swing, and then like get them out real quick and make them walk, right? Yes, I experimented on my children when they were tiny, so and they didn't know any better. So what if I decrease the moment of inertia of the skater by 25%? What would the final angular speed increase by?
25%.
25%. This is just a simple linear relationship, right? Okay. So, if I told you the initial angular speed was 1 radian per second, and we decrease the moment of inertia by 25%, what's the final angular speed? 1.25.
Bam.
Got it? That's the concept, yes. Yes. Well, yeah, I wanted to cover the concepts, but I have a free response that's pretty simple. So if you have time, you might want to try this one. This decreased by 25, so this increased by 25. It's that simple. Okay. Oh, I is this, and it's, remember there was a shape constant, mass and radius, but I'm not gonna actually have you calculate it, not for tomorrow, maybe for the semester.